As we continue to explore the extreme values of functions, we now want to take a look at a function on its entire domain. In a previous video, we discussed using the extreme value theorem to essentially find the absolute extremes for a function on a closed interval. And what we want to now do is talk about an entire function over its entire domain and see if this function has local extrema or absolute extrema. And that's what we're going to do. Let me give you a quick example. So let's consider this function f of x equals 2x squared minus 8x plus 9. Now we know this is a parabola. We know it opens upward. So you can quickly get a mental picture of what this thing looks like, right? It looks like this. And what we know is that there is an absolute extreme value here, which we call the vertex down here. That's what we would call that an absolute minimum. But we also know that this function heads to infinity on both the left and right end. The end of behavior for the function at the positive and negative ends is positive infinity. So there's not going to be an absolute maximum for this function. We go through the same process to locate this vertex, this extreme value. We're going to take the derivative and look for critical points. So we know that the derivative here is 4x minus 8. And remember, to get the critical points, we look for places where the derivative is either equal to 0 or undefined. 4x minus 8 is a linear function. It's defined everywhere. And when we set it equal to 0, we find out that x equals 2. This is a critical point. Sometimes people refer to these as critical numbers. So x equals 2 is the only candidate for an extreme value. We don't have any other critical points, and we know that the end behavior of this function is infinity. And let me formalize what we did to figure that out. When we do the limit as x approaches infinity, in other words, what's happening over here of f of x, we get infinity, right? When you plug infinity into this function, you're going to get infinity. We also do the limit as x approaches infinity, negative infinity of f of x. And again, when you plug negative infinity into this function, you're going to have a behavior where you grow without bound in the positive direction. That's this end. So x equals 2 is the only place where we have a candidate for an extreme value. And we know that it's that minimum spot there. So in terms of extreme values, if you want to locate the absolute minimum, you simply plug 2 into the function. So f of 2, which is the y value, is going to be 8 minus 16, which is negative 8, plus 9, which is 1. So what we've discovered is we have an absolute min at the x value is 2 and the y value is 1. So the absolute minimum is 1, and it occurs at x equals 2. And when the function's familiar, you kind of already know whether it's going to have extreme values like absolute mins, absolute maxes. You know what the end behavior is because you've studied these functions. But what about functions that we're not familiar with? Let me give you an example of one of those. So let's consider the function x squared times the natural log of x. First of all, you need to be aware of the domain of this function. The natural log of x is defined only for x is greater than 0. So our domain is 0, infinity, if we write it in interval notation. This is our domain. So we're only considering numbers that are greater than 0 for this function. And now what we want to find out is, does this function have any extreme values? So one of the things we'll have to do is check the end behavior, and then we'll also look for critical points. So let's start with some end behavior. When I do the limit as x approaches infinity on this thing, of x squared times the natural log of x, this is x squared would be a positive infinity, and then natural log of x as you go to infinity, that's also positive infinity. So this thing's some kind of positive infinity. It's taking off without bound. Now, we're not going to check the end behavior at negative infinity because the function is not defined at negative infinity. It's not defined for anything 0 or below. But what we do need to see is what's happening as we approach 0. So we need to find the limit as x approaches 0 of this thing. Now this limit equals 0. And if you haven't learned L'Hopital's rule yet, it's not obvious that this thing will equal 0. It's an indeterminate form, 0 times negative infinity. But you can peek at the graph of the function, and you can see that as we get close to 0, that this thing is going back to 0. We'll talk about how to achieve this limit algebraically with something called L'Hopital's rule at another time. But for now, peek at the graph and you'll see that this thing goes to 0. Now, let's talk about locating extreme values. So remember that we need to check the critical points. That means we need to get the derivative. This is a product. F of x is formed by a product. So we're going to have to run through the product rule. So the derivative is going to be x squared times 1 over x. That's x squared times the derivative of natural log of x plus 2x times natural log of x. So I just did the u, v, and the vu. uv prime plus vu prime. And we can clean this thing up a little bit. This is going to be x plus 2x natural log of x. And then I'm going to go ahead and factor this thing just because I know I have to set it equal to 0. And it's a little easier to solve an equation that's equal to 0 when the expression's factored. So this is 1 plus 2 natural log of x. Now when I set this thing equal to 0, oops, that is terrible. There we go. I'm going to use that 0 product property from algebra class. When you multiply two things together and the answer is 0, the result is 0, either this one equals 0 or this thing equals 0. And I'm saying this can't be 0 because the domain of this function is 0 to positive infinity, not including 0. So the only way this can equal 0 is if the 1 plus 2 natural log of x equals 0. So that's what I'm going to solve. I'm going to solve 1 plus 2 natural log of x equals 0. When you subtract 1 and divide by 2, let me continue this over here, you get natural log of x equals negative 1/2. And then remember the way you solve a logarithmic equation. You use e. So we're going to raise this to e, and we find out that x equals e to the negative 1/2. You might also think of that as x equals 1 over the square root of e. So that's our critical point. So we know there's either a local or absolute extreme value at x equals 1 over e. The way we find out what the actual value is we plug that thing back into f. So f of 1 over the square root of e, that's going to be, when you plug that into x squared, you get 1 over e. And when you plug that into the natural log of x, you get negative 1/2. Right? We already know that back up here. So the natural log of 1 over e is, 1 over the square root of e is negative 1/2. And so when you do 1 over e times negative 1 over 2, you get negative 1 over 2e. That's our y value. And not only is that a local extreme value, but I claim that that is also an absolute min. It's an absolute minimum value. Now let me tell you why I think that. We know at the ends of this function we are at positive infinity and 0. And both of those are above negative 1 over 2e. And since negative 1 over 2e is the only critical point, it's the only possible extreme value, and it's below what's happening at the end of this function, at the ends. And so this is an absolute min, not just a local min. Now you don't have to just take my word for it. Let's peek at the graph so we can see if we did this whole thing correctly. So here you can see that I've graphed the function, the original function on Desmos. I type that in right here. And I also graph that point that we found, 1 over the square root of e, comma, negative 1 over 2e. That's this guy right here. And in fact, that is the lowest y value on this function. Here's the end behavior that we investigated. This thing's going to positive infinity. And right here, this is that limit that I talked about as x approaches 0. This thing's heading toward the origin. So you can see that we did correctly locate this extreme value, and it is an absolute minimum because it's below all the other y values. So hopefully this gives you an introduction to how we're going to investigate these functions. Essentially, we check the critical points and the end behavior to decide if we have local extrema or absolute extrema. Give the problems a try, and if you need me, you know where to find me. In the meantime, take care.